Hello, everyone. Welcome to the Fireworks webinar on Kimmy K3 on Fireworks. We are going to take a couple minutes to let people shuffle in and get their Zoom registrations active. Make sure we have as many people as we can in here. We want everyone to hear this information. In the meantime, I'm going to go ahead and start sharing my screen. That way, I'm going to also first quit out of my Slack. No one needs to see all the notifications that I get all day long. Great, done. Okay, so if you have been with us before, you welcome back. If you have not been with us before for a webinar for anything like that, welcome for the first time. We are so happy to have you. Right, so we have a bunch of people from the Fireworks team on this call right now. That way we can get questions answered. We can make sure everyone is getting, if they want to participate and ask questions or leave comments, we encourage that, quite frankly. Now, I do want to start by introducing your hosts for today, I myself being one of them. So hi, everyone. My name is Sanan Ozdemir. I am head of AI developer education here at Fireworks. Before that, or in tandem with that, I'm also an AI lecturer, entrepreneur, author. Maybe you've seen some of my lectures on the O'Reilly Safari platform, or you've read one of my I want to say 10 books, but frankly, I can't quite remember on agents or LLMs or data science. And as a recent, employee, having joined Fireworks a couple months ago, I'm so excited to be leading these webinars with you all. And we actually have a special guest today. I'm going to turn it over for just a minute for James to introduce himself, one of our co-founders. James, tell us a little bit about yourself.
Yeah, for sure. Nice to meet you all. My name is James. Like Sanan mentioned, one of the co-founders here at Fireworks. We started this company with a founding team that was a lot of ex-PyTorch people, including myself. So we had a lot of experience in, how do we make deep learning, right, fast and efficient and scalable. This has proved very useful now that we have an LLM industry and LLMs are deep learning, right? So now we make LLMs fast and efficient and scalable. And in addition to that, we are also helping people to use and adapt like LLMs to their specific use cases. So a lot of the content like of this is going to cover, hey, what's the new model, right? What can it do, right? Like how do you actually like make it do what you want it like to do? So I'm really excited with all of the like products we have across inference and training to kind of talk with you all like today and show you like what's possible like with these like open source models.
Thank you, James. And that really sets it up perfectly because part of the moral of today's story is less going to be around, don't get me wrong, we're going to be talking about Kimmy K3. That's the whole purpose of this. But a lot of what we want to get across is every time a new model is released into the wild, and if you didn't know, there's actually been more models released since even Kimmy K3. We want to start providing a framework around how do I think about these model drops. Every time a new model is released from a research lab or from a company, how does that fit into my mental model of where AI is today? And more importantly, how are you using AI today? And I think that's going to be a pretty big distinction between what do you see out in the public, benchmarks and things of that nature, and how do you bring that information back home to your organization to say, this is how we should be using these models in our day-to-day professional life or even personal life, depending on what you're doing. So a lot of our talk track is going to be around just thinking about model releases rather than just every single new model is the latest and greatest at everything in the world. That's not going to be the case. So our agenda today is going to be a quick overview of Kimi K3, again, starting at that kind of high level public benchmark level of what are we even looking at? What does this represent in the landscape? Then we're going to take it one step lower and talk about using Kimi K3, not just on Fireworks. Of course, you're going to use it on Fireworks. It's the best place to use it, but also using Kimi K3 on different types of tasks and how you want to think about those evaluations. Then we're going to have a pretty exciting demo on training Kimi K3, because that's going to be one of the key things that we get across today is not only is Kimi K3 available for you to use today on Fireworks, it is, you'll have fun, but it's also available to train on Fireworks. And that, for me, as a kind of the weirdo in the room, that's the fun part. because that's where you really start to make Kimi K3 your specialized AI. And that concept to me is quite exciting. So I'm excited for that. And then, as always, we'll have open QA at the end. But if you do have questions, please feel free to put them in the chat. We do have the team on hand ready to answer questions, James or myself, depending on who's not talking. We'll also be able to see them and help out where we can. So please ask questions. If you don't get to them immediately, we will do our best to get to them by the open Q&A. So keep them coming. A couple upcoming events, just so you're all aware. This Thursday, yes, in 2 days, we are doing a joint webinar with Arise, and I'll actually bring that up again a little bit later because part of our topic today is going to lead into that. And a kind of a soft announcement here, soft meaning, not to the lovely people in this room, not necessarily to the world yet, is on August 18th, we're going to be running our first cohort of Fireworks Academy, which is going to be a structured learning environment for people to come in and learn, not necessarily just about Kimi K3 or GLM, the latest models, but just inference, AI inference in general, AI training in general. So I'll mention that again by the end, but we have a lot of exciting events coming up. Okay, so we're going to start off with, in case you missed it, Kimi K3. What even is that? How should I be thinking about it? And if you're really coming from scratch here, Kimi, the family of Kimi models, K3 being the latest iteration of Kimi, represents Moonshot AI's flagship open weight model. And generally, there is a difference between open weight and open source. Not every open source or not every open weight model is open source. Not every open source model is open weight. These days, and maybe James, I'm actually curious, if you see the same. I see that conflated a lot. Actually, this morning I was reading an article in the New York Times talking about all open source models, and I was like, they're not technically all open source, but I'm going to let that one slide from the New York Times. So there's definitely some conflation of the two terms, but I'm going to do my best to be as precise as possible. So at the very least, all the models that we are running on Fireworks are open weight. This Kimi K3 does represent a first in a few ways. And one of those firsts is that it is the first open model in the roughly 3 trillion parameter class. It's 2.8 trillion parameters, so just under 3 trillion parameters. Like most models, I mean, frankly, virtually all frontier models these days, it is also a mixture of experts model, meaning that of those 2.8 trillion parameters, not all of those parameters are active while you are inferencing using that LLM. Basically, what that means for your bottom line and for our bottom line that we pass along to you is that we essentially need less compute rather than having to activate all 2.8 trillion parameters at the same time effectively. That would be insane. That would be way too hard. So Mixture of Experts itself is a family of algorithms that are specifically designed, among other things, to reduce the compute needed to do those forward passes, to do that inference of token generation. So expect that almost all, if not actually all, modern frontier AIs are going to be in that family of Mixture of Experts until there's some net new discovery in that field. And James, I'd actually kind of want to turn it over to you to kind of tell us a little bit more about kind of the Mixture of Experts and also maybe some of the more nitty gritty details like the Kimi Delta attention, the native vision, million token context.
Yeah, absolutely. So with respect to mixture of experts, as Sinan mentioned, for a given like token that's going through the model, you don't necessarily need to go touch every single like weight. So compute is lower. However, at the same time, you still need to keep all of the weights for all of the experts somewhere, right? So at Fireworks, basically one thing that we can give you is a scale advantage where we can run these models, right? And we run them with traffic that's going across multiple like customers. So basically the cost of keeping like the like all of the expert weights like in memory is paid once, right? And then kind of divided like across like all of the different customers that are using it, right? So that's how you can kind of get like a scale and cost advantage like concretely like out of this model by coming to like a provider like Fireworks as well. Another thing that I would sort of talk through here is, oh, there's this Kimi Delta attention, right? Okay, well, what does it even mean, right? So like the way that like these LLMs work, right, is you kind of have your text, right? The text is broken up into little pieces, and the pieces are run through the network, right? But of course, when you're reading a sentence, right, or you're reading code or things like that, you're reading each piece like of that text in relation to the other pieces like of that text, right? So I read one sentence and then another sentence. I still have that first sentence in my head, right? I can think about like, what was said like first. So the approach that like these models use for like kind of mixing context is what we would call it, is called that attention like process. Long story short, right? The attention that's typically used, like in these models, is very expensive, right? It's basically saying, okay, well, for each little piece of text, right, I'm going to go and I'm going to look at every single other piece of text, right, that like came before it. Okay. And so this works, right? You kind of don't forget things, right? Because you're going looking, you're rereading like, the entire text like every single time, but it costs a lot, right? It costs a lot in terms of compute. And so like we're talking about cost both in dollar amounts, right? And like we're talking about runtime, right? So it runs slower. So one of the things that Moonshot has like basically innovated here with this delta attention is sort of like, how do we make it so that we don't actually have to go read the entire text like again, right? Every single time like we're generating like the next piece like of the text. And it's basically, how do you actually compress like what you've read so far into a little kernel, right? Like a little kernel of information that you can just kind of like carry forward. You don't need to rederive that like from scratch every single time. This is used in conjunction with the traditional attention like that I mentioned to make it so that the model is both efficient and it can remember like the things that like it saw before.
Yeah, and Kimi Delta Attention KDA is also, among other things, optimized for longer horizon work, which is actually going to lead into one of the benchmarks that I'm about to show you. If you and as James mentioned, the attention mechanism, which has been around for over a decade at this point, even before the attention is all you need paper in 2017. And if I may, the actual architecture of the transformer has, relatively speaking, some of the biggest advancements have come in that kind of squeezing water out of a rock in terms of attention. If you think back to DeepSeek R1, we had multi-latent attention, MLA. Now we have Kimi Delta attention, flash attention. The work that we do in this language processing and how those tokens relate to each other really can make all the difference. Now, coming back to Kimi K3 on Fireworks, we pride ourselves on being day zero providers for a lot of these models, both in inference and in this case also for trainability. So on day zero, the first day that those models weights were released for Kimi K3, it was hosted on Fireworks with 100% US hosted on serverless, 0%, 100% zero data retention. So meaning we don't retain any of your data when you're running through our models. We don't want it. We're not making models. We are here to make this as safe and comfortable as of an experience as possible. And like I said, Kimi K3 is already trainable on our platform. So how does Kimi K3 compare to the Frontier? Now I'm sure you've seen news articles, blog posts, and tweets and LinkedIn posts from all different people around here. And I'll give you kind of a breakdown. To put it simply, Kimi K3 is competitive with closed model Frontier. So if you compare it next to Opus, Fable, GPT 5.6, which are, as of the recording of this webinar, the furthest frontier that Anthropic and OpenAI have put forward, it is frankly comparable. It is actually number one on long context reasoning. Remember when I mentioned that KDA really improved on longer context attention mechanisms? That really shows in a long context reasoning benchmark. It's also number four in GDP val. And I will frankly, points awarded to whoever actually knows what GDP val is, and I'll just give you the answer. It is a benchmark made by OpenAI that is specifically meant to test the AI's performance on economically viable AI. And if you've actually been to some of my lectures before, you've probably heard this rant before, but I'll give you the long story short of it. On OpenAI's charter, they actually define AGI as being AIs better than humans at most economically valuable tasks. So when OpenAI defines AGI in this way and also puts out a benchmark on economically valuable tasks. You can see there's kind of a cross incentive there to say, well, if our models do well on this benchmark, we are kind of proving, quote unquote, that we are achieving AGI by our own definition. That being said, Kimi K3 gets fourth on that benchmark, which is pretty darn good. Now, caveats here, as you should always assume there are caveats in benchmarking. Artificial analysis, which is AA here, in one of their benchmarks called omniscience, which is effectively a factual recall and hallucination benchmark, not only did Kimi get better at recalling facts, it also started hallucinating a little bit more. Now, comparably, you can also see that the frontier closed AI models are also hallucinating. It's not like Kimi K3 is the only model hallucinating here. But this is good. Again, part of the mental model is not every new model is just net better in every way. That just simply can't be how we think about new models coming out, because frankly, it's just not true. So we have to remember to keep them in context in what benchmarks and what applications do they thrive in. Another number one here, it is also number one open model on the front end code arena. So coding is very much in the wheelhouse of Kimi K3. It's actually the first model, open model, to be ahead of every other closed model on that arena. So that's another first for Kimi K3. Now, those are just public benchmarks that you can just find online and see other people reporting. But here at Fireworks, we like to go the extra mile, and we like to do a little bit of work on not a little bit, a lot of work on our own, doing this benchmarking and training. So I'll kind of walk you through a few of these. In one of them, we compared Kimi K3 to Opus 5 in particular. And we found that in general, and again, as always, links on the bottom for everything that I'm citing here, so you can read along if you would like, and you'll get the slides and recording when we're done. Kimi K3 is matching Opus 5's performance at 5x better cost per task, and that term is going to come up again a little bit later. So it's easy to say, as a kind of a general takeaway there, that if you default to K3 for a bulk of your work and rely on a closed model like Opus, where the task demands it, meaning when the task gets a little harder, that's a fair statement. But quite frankly, it's not enough for Fireworks, because we wanted to go one level even deeper than that. So in a separate head-to-head, we kind of upped the ante and said, Opus, fine. But what about Fable? Let's compare Kimi K3 to Fable on coding, and in this case, a legal task over here on the top right. We got for those of you who are remembering my woes from last time with my tablet for drawing, it's not working again, so I will fix that later. Legal tasks and programming tasks. Now, at a glance, you're looking at on the x-axis cost, on the y-axis the solve rate, meaning the performance of that model. In cases like multi-lang, which is multiple programming languages, not like Italian and French, but like Rust versus C, we see that models like Fable are pulling ahead on solve rate, while of course being a little bit more expensive. But even if you dive in on SWE, Software Engineering Benchmark, which was basically equivalent, it was 92.4 versus 92.6. If you break that benchmark down into its smaller subcategories, like symbolic math versus data visualizations, you start to see those gaps re-emerging. So always question, frankly, surface level benchmark reports, not because someone's trying to lie to you, that's not why, but because benchmarks are meant to be publicly held out test sets, which encompass so many different, even in a software engineering benchmark, that can be broken down into several subcategories. So it's almost always going to be worth diving deeper into the subcategories of benchmarking, which frankly, we at Fireworks like to do and report out so that you don't have to if you don't want to. So those swings are quite are fascinating, and I do actually want to turn it over to James in a second, because when we see things like 50x% more cost effective than Fable on tasks like terminal agentic ops, on long agentic loops, can you actually walk us through, James, kind of like the process here and like how Fireworks thinks about doing these benchmarks?
Yeah, definitely. And actually, Sina, can I ask you to go back a slide for a sec?
Absolutely.
Or no, one more. Yeah.
One more.
Yeah. One thing I would point out here, right, is this chart here is something you can think of as like a Pareto chart. And here's what I mean by that. It's an accuracy versus cost chart. So the optimum here is basically you want to be as far left as possible. and as far up as possible. All right. A lot of these here, you'll see, at least like, in this chart, it shows you, well, one option is lower cost and lower accuracy. Another option is higher cost and higher accuracy. But the most interesting part of this chart to me are the comparisons where that's not the case, right? Where you kind of have, instead of the split going, I don't know if this shows up correctly on your side, but from left, bottom left to top right, it goes from bottom right to top left. What this means is that there exists an option, right, that is better across the board, right? It's cheaper and it's better here. And it's very, very interesting, like the results that we see here, right? For Kimi on the terminal and like the legal benchmarks. And then as Sinan, like Anna mentioned, if you break down some of these other categories, you start to see like this effect, like as well, right? You have an option that's actually better, like across the board. Yeah, Sinan, can you go to the next slide? So what this is kind of showing, right, or the last slide is kind of showing is when you take the product of those, right, when you take the product of cost, like by accuracy, you actually find like, some real gold there, right? You can get a lot of performance, like, out of less, like, dollar spend here. Okay, yeah.
Yeah,
Next.
and that dollar spend, and we're going to come back to that because that's a really important, because that's what everyone's thinking. I mean, that's not the only thing you're thinking, but you're thinking, how do I cost effectively use these models to the peak of their performance without peaking my own wallet?
Mhm.
And that's going to get us into a kind of an interesting kind of conversation around routing, which is something that we've been exploring a lot, I mean, for a while at Fireworks, but we're also now starting to productize a lot of our findings to help our customers make these decisions on the fly. So as part of that same research that I was just talking about with Kimi K3 and Fable, we found that after we had run all of these benchmark questions, so that's important. After we had concluded running the benchmarks, we looked back and said, well, if we looked at every single time we gave a task to K3 and Fable, it turned out that depending on the subcategory, legal and coding and so on, if you 72 to 96% of the time, Kimi K3 could solve the task just like Fable could and was cheaper. So for algorithmic learning, for the algorithmic benchmark, it was 96%. On legal, it's starting to show a little bit more of a gap, but still 72% of the times on that legal benchmark, when Kimi K3 was put against Fable, both of them answered correctly, but Kimi would have been cheaper to do it on that model. So it raises the question, and because this is a pretty wide spectrum, from 96 to 72%, how can you know that difference? Well, before we can get to how you can know that difference, I'll kind of wrap that up in a little bit of a bow here. If, again, as a retrospective, after we run these benchmarks, if you could look back and say, knowing what we know after the fact, if we were to have routed it to the right model, meaning we know it will get it right and we know it will be cheaper, that's called oracle routing, by the way. It's because you have perfect knowledge. You are the oracle. You have seen the future. You know what the answer is. Looking back and routing it in that way, what was not surprising was that in every single case, routing would have actually yielded more performance. That's not necessarily true all the time, to be clear, but it's not necessarily surprising that by routing to the right model, which one's going to get it right in the moment. It's not always going to, it's going to be monotonically higher, but generally it's not going to be a huge difference in performance. What is surprising, at least for me, when I read this piece, was that in some cases, in this case, only one of the benchmarks, SWE, the router was actually not only better, but also cheaper. So by routing perfectly, you could actually achieve the cheapest benchmark evaluation and also the best benchmark evaluation. And that's actually surprising, I think, not necessarily in that we didn't expect it to happen. It can happen, but it's not necessarily the thing you expect day to day. But it was really exciting for me and at Fireworks because that implies that if you can make that router as good as possible, then you have a chance to get a performance from your AI system, your ecosystem, not just your AI model anymore, that actually rivals any singular model on its own and can be even cheaper in the long run. Now, as I mentioned, that Oracle routing is a ceiling. It is the theoretical best performance you could possibly get, having knowing in the information ahead of time. We've run the benchmark. Let's do a retrospective and route it to the right way. But that's not possible. Now, if only there was some way of estimating perfect maps that we know exist. Well, we do. It's called deep learning. So meaning what we do at Fireworks is we actually have a product called Fire Router, where we have a custom trained model who is there a priori, so not knowing ahead of time, of course, which model is going to be best, routing work to the most cost-effective model that the router believes will be able to solve that task. Because if the oracle is the ceiling, the challenge is approach that ceiling. And that's what Fire Router is doing, is we are attempting to approach that Oracle routing ceiling of, can we actually route these tasks to the best model at the best time? There's actually a question coming in here, is faster equal better in general, all other things being equal? I'm glad you asked, because what is better is always going to be subjective to a degree. Now, with a benchmark score, generally what better means is solving the tasks at a higher rate, and even that can get a little nuanced as how you're reporting solve rate, or pass at K, or pass caret K, which is even a different metric. There's actually going to be more on that if you take our inference 101 on evaluations. But even that can get pretty nuanced. But how you define better is going to be subjective. Perhaps the workloads that you're running are not that time sensitive. For example, coding tasks. Yes, everyone wants their PR sooner rather than later, but if a model is going to be 30% slower but yield a higher solve rate, I'm willing to wait that 30% longer to make my code the best it can possibly be. So it's not necessarily the same metrics for everyone, and I'm glad you asked. So Fire Router is available today, by the way. You can find it at those links below. And the way it works is every single turn, every single request made in your coding harness. So you come with the coding harness that you're already using, like Claude Code or Cursor or Open Code, whatever it might be. Every time you put a task to that harness, Fire Router will route the task to the what it believes is the right model that can solve that task at the cheapest cost available to you, whether it is an open model on Fireworks or whatever that harness comes with under the hood. James, is there anything you want to say about Fire Router? Because this is for me kind of the exciting part. If Oracle is the ceiling, we got to approach it. What are your thoughts?
Yeah, yeah. I think like here at Fireworks, because we live and breathe LLMs and we see all of these tests and all of these benchmarks, and we have a research team here, I think we're really well positioned to develop that like one hard piece, right? That classifier model that approaches the Oracle here for you all, to use to get higher accuracy and to get like lower cost. So this is a really exciting like project for me and for everyone around the industry to start using.
Yes, I agree. And part of the reason the Fire Router is so interesting, I think, for a lot of us, is it represents a mind shift, a change in the way we think about AI. Having, worked as an ML engineer for over a decade, even the last 5 years more specifically, a lot of my clients would always come to me and say, okay, this new model came out. Should we switch? And that was always such a hard question to answer because, well, it depends on what you're doing. What is better for you? Are you okay with slower and more verbose, or do you want to pay more for a higher solve rate? It's always a conversation. And with routing, that conversation in some ways gets more complicated because you're adding more models into the mix. But in my opinion, it gets simpler because if you accept the fact that models come with their pros and their cons, their strengths and their weaknesses, the question then becomes, which model is right in this moment? And as the library of open and frankly closed, to be clear, as the library of AI models ever expands around the world, we are all going to start to have to make these decisions of, how do I think about this multi-model ecosystem that we are building? All right, so that's going to take us to our next section, which is how do we use K3 on Fireworks? And I'll tell you right now what you can do in the next 50 seconds. 50 seconds after you're done watching our beautiful webinar, is that you can go on our inference platform, our serverless inference platform right now, and start using Kimi K3. And by the way, if you remember earlier when I said there's actually been more releases even since Kimi K3, you'll find almost every single frontier model that is as open weight, you will find on Fireworks. That includes also in the last week DeepSeek V4, which perhaps we'll do a webinar on that at some point. But if we were going to do a webinar on every single model, we'd be doing a webinar every 3 days, it feels like, which, hey, you know what, I'm down. But that being said, using these open models on our inference platform is truly simple and is as easy as a one-line change if you're already using an OpenAI compatible endpoint. So if you're using OpenAI, for example, it's going to be effectively a one-line change to use Fireworks. And then you have your choice of all of the models that we have on our library. And of course, we have tiers, our standard tier, which is what you're looking at on the screen, price-wise. And also that's the default of what you'll get by just using our serverless inference. But we also have different tiers of use like priority and fast, depending on what it is that you're looking for. We also have not necessarily for all our models, because you can dedicatedly deploy most of our models and frankly choose the region that is supported. But in general, for Kimi K3 especially, it is 100% US hosted on our serverless. And again, as always, zero data retention by default. That is non-negotiable as far as I'm concerned. Now, I could throw a table like this at you, and I just did, about token prices. And the reason I'm showing this to you is to kind of show you in comparison where Kimi K3 sits. So above Kimi K3, kind of price-wise, you see models like Opus, Sol, Fable 5, no surprise. But look right above Kimi K3, you'll see Claude Sonnet, which is why often you'll see this phrase, Sonnet level prices for or Opus or Fable level intelligence. And that is again a fair first sentence of the essay that is Kimi K3, because it is priced identically to Claude Sonnet, where we've already shown you that the performance rivals not Sonnet, but Opus or Fable. And under Kimi K3, we have some other models also in the frontier class like Minimax, GLM, and DeepSeek coming in at a little bit cheaper. Now, which model you pick or route to is going to also depend on how much money you're trying to save versus how much performance you're willing to leave on that table. And just like our tiers, we have other options for different pricing, like, for example, cached tokens, which is not necessarily something that only Fireworks offers. Many AI providers offer cash pricing. And if you're unfamiliar with cash pricing, basically what that means is if you reuse the same input tokens, which if you're going in an agentic loop over and over again on multiple tool calls, you implicitly are reusing a lot of input tokens, that cached token really kicks in as the model goes into longer and longer horizon work. But this sticker price, if you will, for token cost is becoming a little bit less understandable, quite frankly. In my day, we measure them by the 1,000 tokens. Now we measure them the millions of tokens. And even today, that kind of rings a little bit hollow. Because when I tell someone this is the price for 1,000,000 tokens, almost always their first question is, what is 1,000,000 tokens? Is my conversation with Claude 1,000,000 tokens? What does 1,000,000 tokens mean to me? And that's a fair question, which is why, again, both at Fireworks and around the globe, we're starting to think more about AI in cost per task, which, as with any talk with me, has its pros and cons. Because on the pro side, it makes more sense. If you're thinking about, well, this is the task I want you to do, how much will that cost? As opposed to how many millions of tokens will it take to get that task across. So I can talk about 52 cents per task or 6 cents per task, and that makes more sense to the person listening. The con, however, is, well, what task? Software engineering tasks, you'll have, therapy tasks, legal tasks. What tasks are you talking about? Each one is going to come with different nuances. It's going to be shorter or longer, and that just requires more effort to get to that number. And even then, quite frankly, you have volatility in the model itself. It's no secret that these LLMs are non-deterministic, meaning if you put in the same input, you're going to get, all things held equal, the different outputs out every single time unless you actively do something to change the output generation. So if that's true, you would expect that every time you give that model a legal task, whether it's Fable or Kimi K3, it's going to get a different answer or at least go about it in a different way, yielding a different trace, different number of tokens, a different cost. So it's nice to explain to someone the cost per task, but frankly, it can be difficult to calculate because everyone's running different tasks. Now, what we can say as a kind of an aggregate is, and this is something that artificial analysis AA also will report, is that open models, Kimi K3 included, tend to be a little verbose, meaning they tend to output more tokens, either in the reasoning or in the kind of the raw output content side of things, than their closed model cousins. Now, usually that verbosity is almost, I mean, not just usually, but almost always, that verbosity is counter affected by the lower token cost for that performance level that you're looking for, and also the caching that we talked about in the last slide. So as always, there's a lot of variables that goes into this, but in general, what you're looking for is a way to measure the amount of money it takes to solve a certain task. And as the numbers you're looking at on the screen here, these are numbers that Fireworks will also report. And for more on evaluations, we have more cookbooks coming out on how to measure this yourself for a custom evaluation set. And again, in Fireworks Academy, it's going to be a big topic as well. All right, so we're going to get to our first example here. We actually have two code samples that I want to run through. And because we want to keep these things as tight as possible and answering these questions, I'm going to show you the code with a promise that you'll be able to see that code on our cookbook, on our GitHub after the fact. So you can run along or run along, walk through our code after the fact as well. And for our major code snippet that I'm going to show at the end, I've already recorded a 30-minute video of me walking through the code sample. So you can listen to the dulcet tones of my New Jersey voice whenever you want, which I think is actually a great plus. The task at hand. If you've read my book on agentic AI, my most recent one, you've seen this example. And I really like this example because it's pretty realistic in the sense that almost all agentic use cases I've seen my colleagues, my friends, my clients run at some point requires the AI to look up some information or interact with some database in some capacity and look up information about that database so that it can chain together a lookup call and an action call. And this data set, or this task rather, is called agentic text to SQL, which basically means I'm going to give an agent, an LLM with tools, I'm going to give an agent a task that requires looking information up in a SQL database. Easy peasy, right? I give it a natural language task. It writes SQL, it runs the SQL, it uses the answer that it gets back from the table to answer my question. Easy enough. It's realistic. There's also a success metric that I can pretty easily quantify without an LLM judge. Again, more on LLM judges on our future webinars and content on evaluations. But for this case, I said an LLM will not be judging this. I am simply going to look at the SQL that it wrote, the SQL that it used to answer the question, and I'm going to compare the rows that it spit out with the ground truth rows and give a score on, are you finding the right data that I'm expecting? Is it a perfect evaluation? No, but it will get the job done. The database is actually coming from a benchmark called BIRD, the Big Bench for Large-Scale Database Grounded Text to SQL. If you've never heard of it, I don't blame you. It's not a newsworthy headline, I would argue, but it is a real benchmark. And the reason I love this benchmark, again, if you've heard this from me before, I apologize, is that not only is it, here's my question, write some SQL, that's fine, but if you've ever worked with a database over time before, you'll know that sometimes your company drifts forward while your database tables sometimes can stay a little stagnant. So this benchmark comes with evidence, meaning tribal knowledge about the database that would help you write the correct SQL on your first or second pass. And that for me is interesting because, again, that's pretty realistic. You have this information about the database that is natural language that would help someone writing SQL. So our agent is going to be in charge of actually look, and I'll start switching over here, actually looking up the evidence that it has while also running the SQL. So this coding notebook is relatively simple. It's just going to set up the agent, and we're going to actually see this agent again in our next coding example. So here, what I'll show is the database that you need to use is run by this. And again, this will be in the cookbook, so you can run this yourself. There's a file called prepare data, which is going to download all the data that you need and put it in the right format in a vector database specifically for the evidence and setting up the SQL tables for the LLM to actually use. So all this notebook is going to do is set up an agent and run it through a bunch of different models, including Kimi K3, DeepSeek V4 Flash, the newest one that came out after Kimi K3, GLM 5.2, and then also 3 models from OpenAI, just to keep things fair, but also light. I didn't want to bring in Gemini, Anthropic, and other models. And we already talked about Anthropic, and I wanted to give OpenAI their due as well. So the tools here are simply going to be fetch the schema of the database. I'm not even going to put in the prompt. It has a tool to fetch the schema if it wants to look at it. It can look up evidence if it wants to do so, and it can run SQL against the database. That's it. Otherwise, it can talk to us, as a chatbot wants to do, but it can also use one or more of these 3 tools in order to solve its task. So some helper functions to load up the vector store, actually implement the tool functions here. That's all this code is doing. This is the actual loop. Now, could we have used LangChain's create agent, for example, or crew AI or AutoGen or ADK? Sure, but just to kind of iterate as many times as possible how simple the tool calling loop truly is. All that really happens in again, in a very simple tool calling agentic loop, your model is what you instantiate. Here I'll instantiate through LangChain's chat OpenAI with a specific base URL pointing to Fireworks for Fireworks models and back to standard OpenAI if you're just using them. We give it our messages. We iterate over a maximum number of turns just to make sure no one goes off the rails. If there are tool calls, we execute them and append a tool message back into the context window. And we don't stop until the LLM stops calling tools. That's the end of its turn, and hopefully it's answered our question. So if you want to look at it for one specific model, this, for example, would be the Kimi K3 doing one of those trajectories. So first, it calls the database schema. It gets the schema back from the tool. Then it looks up some evidence. It gets back some information about the thing that it looked up. Then it runs some SQL against the database. It gets back an answer. It apparently ran another piece of SQL to get back an answer. And then finally, it answers my question at the end of the trajectory. That's all. So then, to see how these models compare against each other, all I have to do is pick an eval set, and this is a benchmark, so I'm using the samples from the benchmark, and I'm going to run it for 10 total questions, but I'm going to report the solve rate, meaning how often it found the exact rows I was looking for, at 1, 3, 5, and 10. And I'm going to skip to the graph here so you can see what I mean by that. I'll say this graph in a different way. Excuse me. If you only chose one question from the benchmark and asked each of our models, GLM would have gotten a 0, Kimi would have gotten a 0, everyone else would have gotten 100%. But that's clearly not true. So as you add more data to your eval set, your test set rather, your holdout benchmark, if you will, you start to approach a more standard flat curve of, well, where does this model actually perform in rankings to the rest of the models? Now, to be very, very clear, 10 questions does not a benchmark make, to be very, very clear. This is meant to be for demonstrative purposes to show that as you add data to your test set, you want to see this kind of stabilizing of performance, and in this case, the average score that it's getting, or in fact, the solve rate. Speaking of solve rate, and I'll show that in the next graph here, if you compare the six models that we had on this test set, GLM got 20%, DeepSeek got 40, Kimi got 40, and the GPT models got 60, 70, and 70. Oh no, that's not really good for Kimi K3, is it? Well, luckily, in our next coding notebook, we're going to fix that by helping Kimi K3 actually do better at that task by post-training it on our training API. So let's go ahead and go back to those slides here. James, did you actually want to say anything about this? Just any thoughts here?
Yeah, no, I think it's just a good setup for our post training. So happy, like excited to dive into it.
Let's do it. James is excited, as am I. Now, if you were at our last webinar, which was about fine tuning, these slides are going to be a little bit of a refresher. So I'm going to go through them a little bit quicker than I did in the last webinar. And if you want to learn more about that, you can watch our last webinar. The video's on YouTube, and we'll put a link to it in the follow-up email after this. Modern LLMs are trained in effectively three main phases: pre-training. You know what, James? I'm going to tap you again. What do you call them? Because I've heard it called mid-training. I've heard it called supervised training. What do you call the middle tier, the middle
Yeah.
box?
The middle tier has kind of a nebulous definition. It's one of
Yeah.
those things where it's a continuous spectrum, and where do you draw the line there? Mid training, yeah, sure. You could call it that. There's also continued
Instruction
training.
training, instruction tuning, I've heard it.
Yeah, yeah. I guess maybe continued pre-training might be another thing between one and two here, right? There's
Well,
also
continued pre-training would be like
yeah,
the active pre-training, but just after you've done. You
yeah,
see our point. We
yeah.
got two ML engineers on the call here, and even we're kind of like, what do you call it? Like we call it something different, you call it something different. But the real thing to take away here is that there's three phases. Let's call them pre-training, mid-training, post-training. The general concepts here are pre-training is where, and I've heard this term used, is where LLMs learn the world. The general idea here is that without being a chatbot, the LLM is not expected to be a chatbot here. The LLM is simply expected to predict the next token given whatever, whether that's a common crawl data set, which is one of the world's largest open source repositories of pre-training information for LLMs, or book corpus, which if you've never heard of that one before, that was actually a very early pre-training data set. It's actually what the BERT model, the bidirectional encoder representation from transformers model in 2018, was pre-trained on book corpus and English Wikipedia at the time, which kind of pales in comparison to the large amounts of pre-training data that research labs use today. Then we have supervised training or mid-training, in which you teach the LLM to be a chatbot. And if you were at the webinar roughly a month ago on fine tuning, you heard my whole spiel on why this message standard? Well, because Sam Altman said so, quite frankly. We kind of settled on this format after OpenAI popularized the role, the assistant, the system, the user, and now the tool messages. A lot of that is just industry standard, but you should know that to the hardcore researcher, this is not set in stone. In fact, if you remember from the last webinar, some companies like Google, when they put out their open weight models like Gemma, they put out both their instruction trained model, which they label as IT, which does not stand for Italian, it's instruction, but they also put out their only pre-trained version of Gemma. So that Gemma is not a chatbot. It does not care about your message standard. It will not follow it because it has only been pre-trained. And that provides a blank canvas, frankly, for researchers to do whatever they want. But most people want a chatbot. And that's where supervised training or mid-training teaches the model to be a chatbot and follow this standard that is basically drilled into its head over and over again, i.e., trained on a loss function to replicate this structure. And then we test it on generalizing its capacity to answer questions in that format on a test set. And then we have post-training, which comes after pre and mid-training, in which the model is already a chatbot, to be clear. The model will, for the most part, follow your instructional data set and follow your instructional format. That's taken care of. But where post-training really picks up the slack is that it really nudges the model to be more preferred in some sense of that word or aligned in some sense of that word. So the takeaway in post training is that instead of showing the model the right answers to questions, we instead usually turn to a technique called reinforcement learning, in which the model is asked to try something, do something. You give the model a task and say, try this. And you let the model try that thing. That's called a rollout. You let the model do its thing, wait, and when the model is done, you come back and give it a grade. Good, bad, something in between. How well did you do at solving this task? And that's subjective. What do you mean by how well? Did you get the right answer? Was the outcome correct? Did you follow the steps I asked you to? Did you follow the behavior I requested? Did you take an efficient set of steps to get there? Was your trajectory aligned to the task? That can be pretty subjective. But in general, you have to give some reward to reinforce the behaviors that you are looking for in reinforcement learning. So you let the model observe a task, you let it act on that task, you reward its action on that task. The model will then update to hopefully achieve higher rewards on its next step. And you do this over and over and over again, which could be for weeks or months in some cases if you're talking about frontier models, or in our case today, it's going to take about 40 minutes when we post-train Kimi K3. So there's definitely a spectrum of how long this takes, but this is doable on Fireworks infrastructure in the afternoon, depending on what it is exactly that you're doing. In our case, definitely can be done in an afternoon. And the reason we do this reinforcement learning is, for, among other reasons, is exploration. We want the model to try things. In some ways, we want the model to fail because we tell it that was bad and it will avoid that behavior in the future. So this is no longer just about showing the AI the right answer. It's about reinforcing behavior that we want it to pursue and non-reinforcing behavior, actively discouraging behavior we want it to avoid. Also from our fine, James, did you want to add to that?
Yeah, no, I think this is good. I can go into Laura if you want.
Yes, please. Yes, please.
Yeah. So I think Sanan has covered like the training process from the algorithmic perspective really well so far. I'm going to dive into a little bit about the model perspective and like what are the implications of that on, sort of cost, right? And like the performance of actually training like one of these LLM models. So we said earlier that Kimi K3 was a 3 trillion parameter model, right? Terabytes and terabytes like of weights. Well, what if I want to train it, right? What if I want to do reinforcement learning or supervised fine tuning, all of that? Do I need to like, keep terabytes of weights and spend the compute, right, to like update those? Or is there a cheaper and is there a faster like way of doing this? Turns out there is. And this is called low rank approximation. And low rank approximation actually applies both in training and inference, but also sort of start out like, with talking about it from like the training perspective. So the idea is that you have like a smaller sidecar of weights on the order of megabytes in scale that you're actually updating. And this sidecar of weights is additive to the existing capability and the existing weights that the model has already. And in fact, I mean this literally. You see on the slide, there's a plus sign here. It turns out you can add functionality to the model by using a mathematical addition operation. This is kind of a fascinating property of like LLMs are mathematical objects that compose linear and nonlinear operations. Well, it turns out you can modify their behavior like by using an addition operation here. A good analogy for this is there's the scene in The Matrix, I forget which one, but Neo is sort of training with Morpheus, right? And then suddenly oh, I know Kung Fu, right? Like, that capability was added like to him. This is exactly what's happening, like with like using Allura to actually train and modify an LLM's behavior. Then the second part here is how do we actually get that cost savings? I mentioned the sidecar weights were only megabytes. Well, how do we modify terabytes worth of weights with only megabytes worth of data here? And this is the core of what this low rank approximation is. Here's an analogy I can give you. For the most part, we all agree that the Earth is a sphere. Okay. But when we reason about the geography of the Earth, we actually think of it in two dimensions. We don't need all of the information of all of the three dimensions. If I need to get to work, if I need to take the subway, things like that, I can look at a two-dimensional projection of the three-dimensional reality and get my tasks done using that. That's exactly what's happening here as well. For most tasks, you don't actually need all of the degrees of freedom that 3 trillion parameters of weights give you. You project down into a smaller space, right? Get your work done there, and then project back up, like to the full the size of the model here. So this gives us a ton of advantages. We have a serverless training product that has similar of the scale advantages that I mentioned earlier for, kind of shared like inference. You get that as well for training. You start up a session, it goes on a shared trainer. All of the different like customers share the base weights, but then they're all working on like their own adapters on top. These megabytes like payloads, right? That they can just like update like very cheaply here. And then, so for how does the quality compare, right? If I were to tune the whole model versus like if I were to use this LoRa approach, can I actually get the same type of quality that like I would get with full parameter training? Well, it turns out the answer is most of the time. And an overwhelming majority like of the time. And there's other information theoretical arguments that all the researchers like talk about, but we actually put this into practice. We put out this blog. We basically said, let's take 3 novel tasks that the models don't know how to do at all, right? They have to learn some generalized like procedure for placing wires on a chip or allocating registers like in a compiler or like learning to be like a computer, like essentially like an interpreter. And here's what we actually found. We found that before we even get to limitations that are imposed by the reduced capacity, like of the LoRa adapter, there's other things that we can try and often close almost or like literally the entirety like of the gap between LoRa and full parameter training. These being number one, do you have the right data coverage, right? Maybe you just need to modify your data set and show the model like different examples to get it to learn the right thing. Number two, do we need to tune the recipe, tune the learning rate? You have all these knobs you can pull, right? And then once we get there, potentially without even switching to full parameter training, we can change the rank, right? Change the dimension to which the LoRa's are projecting to give it a little more capacity, right? And what we found is in pretty much every case, you can make the LoRa's work just as well and much cheaper, both in the training and inference.
Yeah, and what is exciting about, I mean, when James talks about like the serverless training API, and I'm going to show that in just a second, it truly represents one of the fastest ways to get started with and cost effectively post train models as big as K3. And if you've looked at my Twitter recently, I put out a little meme where I said LoRa is more interesting and important than the transformer. Changed my mind. I mean that wholeheartedly because low rank adaptation is a technique that works on virtually any deep learning model, not just the transformer. So eventually, if and when we move beyond the transformer, and there's already evidence that people are working on diffusion OLM, state space models, so on and so forth. LoRa will still be there to help people train those models more effectively. And that it represents this flywheel of specialized intelligence that if I have to pound something into your head today, it's going to be that. And to be truly AI native and no longer dependent on other people's AI models and ecosystems, you need to be someone who is not only training models, deploying them, monitoring them, evaluating them, collecting that feedback, and retraining them over and over and over again. This concept that training a model once is fun, it's interesting, and it will give you benefits if you do it right, and using the right experiments, as James mentioned. But you're not done. That's not the end of the story because your model might not drift, the weights are constant, but your environment will shift. The data will shift around that model. And if your model's performance on the environment will start to change over time, and you want to use that evaluation data as future training data to keep continually updating that model so that you are totally in control and your model is moving at the speed of your changing intelligence. More on that in our later, especially in Fireworks Academy. This concept of specialized intelligence as a combination of both inference evaluations and training is going to be one of the biggest drum beats that you'll hear from myself and us at Fireworks on how do you truly become AI native. Which brings us to our final code sample of the day. Task is the same. We're going to take that same exact agent that we talked about previously. We're going to take that same exact data set I talked about previously with more examples. We're going to take that same exact model that we've been talking about, Kimi K3, who already has strong SQL tool calling abilities out of the box, as we've been saying it rivals Opus, Fable, and GPT in many ways. But what we're going to do is we're going to update this model through reinforcement learning, through post-training, in order to teach Kimi K3 to be better at our task. And our task today is represented by Bird. So reinforcement learning is going to sharpen the capabilities that Kimi K3 already has into doing it in the way that we are expecting for our task. Now, our choice of reward here, and I could give you even more blog posts about how to choose reward systems and the difference between dense versus sparse rewards in a reinforcement learning environment. In our case, it's going to be dense in the sense that it's not just going to be thumbs down or thumbs up. Thumbs down is SQL doesn't work, it errors out, or does not give any of the right rows that we were expecting. A one is everything that you said, order aside, is correct. You are getting the right data that I was expecting you to get by the end of this conversation. Partial credit is also allowed if the model gets some of the data that we were expecting, but not all. So it's going to be mostly sparse. There's going to be a lot of zeros and ones and that we give, but there is going to be something in the middle. And whether or not you include that something in the middle is a choice, a choice in your reward system. And one of our recent blogs on reward design talks about the differences between dense and sparse rewards and how that is not necessarily going to make or break your training, but at the very least, it is going to change the way that your model learns. And sometimes it'll be smoother, sometimes it's going to take a little bit longer and be a little bit more jagged, but a lot of that comes down to your reward design. All right, so let us take a look at our next example. This is the notebook that I have a 30-minute video on on our docs. If you really want to walk me through, have me walk through it step by step. For the sake of time today, I don't need you all to listen to me opine over the next 30 minutes about all this code, but I'm going to give you the main beats here. So just like in our last notebook, we're going to be setting up our helper functions, making sure that we have our imports correct, the data is in the right place. If not, run the prepared data.py. And then we're going to have some of our knobs that James was referring to. And in my video, I talk about this, but these knobs that you're looking at here, the values that you're seeing, these just happen to be the last ones I ran. I'll tell you right now, the first number I tried here was 8. Didn't work. Just straight up didn't really move the needle in any way whatsoever. Then I tried 16, then I tried 32, then I tried 64, and I was starting to see the results that I was expecting. Similarly, learning rate down here is one that James mentioned as well. And by the way, in the video, I go over all of these. So if you're looking for an explanation on all of these parameters, I would check out the cookbook and the videos about this particular code notebook. This is one that James mentioned. This is how fast, effectively, should these weight changes, how big of a weight change should we get every single step of the way? These numbers are small. 8 times 10 to the negative 5 is small. But I'll tell you right now, the first number I tried, I'll tell you, was 8 times lower, 1 times 10 to the negative 5. So you are going to want to try different parameter values because I didn't just guess these. That's not how this works. I had a gut feeling. I tried a few different options. After 4 different combinations, roughly, I finally started getting the results I was looking for, but it's going to be a little bit of experimentation. And with serverless training, again, the idea that you don't have to spin up dedicated compute to run this post-training, which is one of the biggest takeaways of serverless training. You don't have to wait and pay for this huge cluster of GPUs to be all yours, even when you're not using them to its fullest capacity. You're still experimenting with some things while you're paying, by the minute, by the hour for GPUs. With serverless training, that doesn't happen. You pay per token. So when you connect to your serverless session, you're paying for the amount of tokens that you're training with, not necessarily for the actual compute by the hour. And because that's true, you frankly get to try more knobs and levers at a faster rate than you could before. Because if you're not worried about dedicated compute, you can be worried about what is the right learning rate. Does my data have the right coverage? Is my training recipe the right one? Those are the questions you should be asking yourself, not can I get a GPU at this time, at this accelerator count, so on and so forth. So our agent, again, exactly the same. Same tool sets. This is a description of the reward system where it's going to be between 0 and 1, a bad SQL, a good SQL, and something in between. The same tools as before. Again, I cannot stress, it is exactly the same agent otherwise. Same model, give me K3 in this case, same tools, same data set, same benchmark. The only, and again, the video will have a lot more on this, the big kind of nuances here is the type of algorithm that we're going to use for reinforcement learning. This one is going to use something called Group Relative Policy Optimization, aka GRPO, popularized by the DeepSeek team. It is basically going to have for every task, the model is going to do several rollouts, several actions on that task in parallel, in the sense that they're going to be independent of one another, is what I mean. It's going to try that task, let's say 8 times. Then it's going to literally do effectively a z-score to relatively rank the rewards or advantages to rank them on the best rollout and the worst rollout. If those rollouts, for example, were varied in nature, they give different scores, that's good. Because again, we can say, don't do these, but instead do these. And we want to give the model, again, we almost want the model to fail in a way so that we can say, don't do that. But we also want it to succeed so we could say, do that. If the model is consistently getting everything wrong, reinforcement learning is probably not going to be your best bet, because what you really might need to do is go back and do some more mid-training to say, well, hey, you clearly don't even understand what the heck is going on here. I'm going to show you some correct examples so that at the very least, you can directionally get on the same page as me, or on policy, as the term of art would be. So once that model can do the task, maybe not consistently or reliably, reinforcement learning is going to be there to pick up the slack and say, great, now you can do it sometimes, you can't do it some other times. Now I can reinforce the behavior when you do it. So here is where I actually run the episode, meaning run one of those rollouts. And again, you're going to notice effectively the same exact tool calling loop, just like you saw before. I am going to be grabbing some things I need for GRPO in the specific loss function that I'm using, like the log probs from the tokens and things of that nature. But again, I'm running my rollouts. I'm giving a way to get the answer to my question, how well the model did. Then I can actually run my loop. So I have a holdout set of 60 examples, but I'm going to run over a separate training set to update the model over a number of steps that I choose. I believe I chose 12 in this case that I finally ended up with. So only 12 times are we going to update the weights of our adapter. This is using Laura. Remember, I set the rank above to 64 dimensions. So for 12 steps, it's going to do rollouts, get graded, accumulate gradients, and then eventually update the weights so that it tries to get more rewards the next step. So we have a training set and a testing set. It's learning from the training set, but it's being evaluated on a holdout set that is different from the training set, so we can see how well its learning generalizes to unseen data. More to be said about that in terms of proper machine learning diets, but that's the general idea, is that you don't want to test your model on the data you also trained it on. That's not fair. That's like me saying, read this book and then recite it to me. Oh, wow, you remember the book? Great. No, I have to ask you questions about that book you haven't seen yet. I can't just give you the practice questions in the textbook, which you've already seen and solved for yourself. So We do some concurrency here because I like things done in parallel. There is a built-in mechanism for the retries to happen. If at parallel you hit a rate limit, for example, automatic retries are built into the system, so don't worry about that. We calculate our scores every so often so we can see how well it's going. And frankly, I'm going to skip right to the main piece de resistance here, which is over 12 steps. We can see, I'll point out two main curves. Look at the dotted blue jagged curve. That's the average reward of the training set. Meaning, as it's going through the training set, it's getting different batches of data to learn from. It's every single batch of data is different from the last batch. So it may not be able to transfer the knowledge it just learned step by step. So we do expect some jaggedness, to be very clear, but directionally we expect it to go up over time, which we are seeing. It's this green line I care the most about. That's the holdout set. This solid green line here is the solve rate of the holdout set over time. And if you notice, the solve rate, if you remember from the last notebook, starts at around 40%, which again, 10 examples in that first notebook is definitely not enough to make a concrete judgment on that benchmark. But it does seem directionally correct with what we're seeing here. Roughly, it's starting around a 40% solve rate before we did anything off the shelf. 12 steps later, and I mean this, about 40 minutes later, this model is now getting close to 80% solve rate on my 60 holdout examples. I mean, James, I'm gonna keep looking in shock while you maybe comment on this as well. Because how do you feel about that?
I mean, it makes sense. Like this is the kind of things you can do with training. It's amazing.
Agreed. And again, 40 minutes later, less than an hour later, our solve rate went from 35 to 80%. Our average reward, which is including the partial rewards, went from 40 to 80, and everything looks great. So coming back to our slides here, and we'll get to some questions in just a moment here, because we're basically wrapping up here, folks, and we'll get to some more of your questions. The results are pretty telling in the sense that I can't promise you that if you run reinforcement learning today on whatever task you're doing, whatever model you're doing, whatever training data you're using, I can't promise you a pretty graph like this. But I'll tell you what I can promise you. I can promise you that Fireworks is going to give you the means to experiment to your heart's content. Because as you are trying different data sets, different models, different tool sets, different harnesses, different ranks, different learning rates, different learning rate schedulers, if that means something to you for different knobs that you have available to you. Fireworks will make that easier than anyone else I have seen on the market, especially when training these huge frontier class models like Kimi K3. And when you look at these benchmark scores, you should be thinking about A, routing. How do I think about the right model for the right task in the right moment? But you should also be thinking about, well, hold on, I want my AI model. Where does my intelligence fit into this equation? I don't want to just prompt things and hope they get better. How do I actually imbue this model with my specialized intelligence so that I can use it in perpetuity? That's what the demo we just saw. That's the real magic there, is that you can start to own those weights and all the inference that goes into hosting those weights directly with Fireworks. So given that, we have plenty of more examples on our cookbook. Here's a giant QR code. If you're looking at it on my screen, it's quite large, staring me in the face. But more than just frankly, the more complicated examples like the ones I just showed you, we also have things like supervised fine tuning as an example, direct preference optimization or DPO as an example. There's other reinforcement learning examples on there. And frankly, as always, if you tell us what you want to see, we want to build it, because the point of the cookbook is to get you all comfortable with coding and working with Fireworks, both inference and training, so that you can have the easiest experiences possible, either coding this yourself or more likely pointing your agent at our cookbook and saying, please learn from this and code the thing that I am looking for. So with that, we're going to turn things over to Q&A. I'm going to get off a full screen here just so I can pull up any links just in case someone asks about it. James, have you been looking in the Q&A? Any good ones we should answer first? Because I see many questions we can start
Yeah.
answering.
Yeah. I think I just answered one about like, what is the actual update? Like what is LoRa doing? And I think it elucidates a point that I actually neglected to mention during my section, which is that when you train a LoRa adapter, right, and then you have this adapter which changes the behavior like of the model, you kind of have two options, right? One of which is you can take that adapter and you can do some multiplication to update like the actual like base model weight, right? That's called merging. Like we call that merging on our platform. We support that, kind of live, right? Like in inference, you can bring up a deployment and merge the weights in and like run it just as if it were like your own base model. The other is multi-LoRa. And this is really interesting, and it touches on like how LoRa also has advantages like at the inference side. It turns out that these adapters, right, like all are basically computing an update vector in activation space. And what I mean by that is just like, that plus, remember what I was talking about earlier, right? So you can actually run multiple of these on the same base model. And you can run them at the same time and efficiently on the same GPUs. So the concept of multi-LoRa, that's sort of like we Fireworks or the provider stands up like the model, but then many different customers can have their different LoRa adapters all stacked up, like and
Mhm.
computing like their own customized like updates on the same base model weights. Right. So there's that scale advantage as well, right? Where you don't need to run terabytes of weights. You don't need to run all of this like compute. You can sort of like share that, right, and then apply like your adapters like updates like to get your own customized model.
And you'll never believe this, James. There's a multi-LoRa case study in the cookbook waiting for people to look at using Amazon's very large multi-intent database from Hugging Face. So if you want examples on multi-LoRa, we got those in the cookbook as well. Another question that I saw in the Q&A here, the held out solve rate peaks around step 11 and then slightly declines, although the reward remains high, which is true to like 1 or 2 percentage points. Agreed. Given that the held out set contains only 60 questions, how do you distinguish ordinary evaluation variance from the model beginning to optimize the reward without improving actual task completion? James, actually, I would love to throw that to you. I can also add some color there, but what do you think?
Sorry, I'll be honest. I was responding to Slack just
You're
now.
totally fine. We
Yeah,
got we
yeah,
got questions coming in. So I'll take a stab at this. So when we're talking about the holdout set only having 60 questions, there is always going to be a case that your data set, your training and testing set should be as big as possible. Yes and no. More data tends to be better, don't get me wrong. But what is more important is data coverage, meaning your data is representative of what it is you're trying to do and covers the gaps and the gray areas you want your model to see and therefore be better at going forward. Now, earlier I also mentioned that it's a lot more complicated than just solve rate. It's a good high level number to show people like, look, it's getting better at solving things. But you also want to understand, to your point, variance. For example, if I ask this new model the same question 10 times. Of those 10 times, how many times did it get it right? So you can start to understand not just the variance across covered data, but also variance across single task repeated over and over again. So this is not meant to be a production ready evaluation harness for what it looks like to evaluate that post-train model. A lot of that is done on our blogs. But by doing the holdout set at all, you are on the right track because you are testing the model's ability to take what it learned from the training data and transfer it over to a holdout set and still see it doubling in performance as well. That's going to be the best first thing you can do. I think we have time for 1 or 2 more questions.
Can I springboard on
Please,
top of
please,
that?
please,
I just
please.
want to like say that like if you look at the three tools to try, like but to compare LoRa versus full parameter fine tuning, there's one example in there which I kind of mentioned, which was the language interpreter. This is a very interpretable, so to speak, like example of how do you actually train a model like to generalize beyond like what it has seen like in the training data, right? And what I mean by that is, for example, if you train it to execute 16 instructions and you try to feed it 32 instructions, what does it do? That gives you some signal, right? Because there is like, a specific function, right? A reusable function that works for infant, right? theoretically instructions that it could work on. But it's sort of part of the experimentation process of like feeding the model or like the training process the right data, tuning the recipe, like dialing in like the capacity like of the model and doing all these sorts of things so that you can get the model like to actually learn quote unquote what's the ideal like the platonically correct function that you're trying to teach it.
I like that. Platonic. I don't think I've heard that. I know what you mean. This is kind of funny to hear it say that said that way.
Yeah.
Another question here. Uh, where to go? Where to go? Here we go. How can we measure the reliability of reward models? Ooh. That's a good one. Reliability of reward models, again, at a theoretical level, we're talking about um, is the reward measuring the right thing? Obviously, that's very vague. But what that kind of comes down to is there are you measuring the agent or LLM in whatever that you're doing? Are you measuring the LLM in a way that matches how that model would be evaluated in production? So in our case, with the SQL reward, when I gave it credit for getting the right data from the database, I will argue to myself that that's not the best, frankly, reward signal that I could have chosen. Because what if it got the right data from the database, but didn't answer the question correctly because the question involved a calculation? So there's always going to be some gap in how you are rewarding the model and what the model is doing and what the model is pursuing. And the big trouble that you'll have is as you add more and more of these independent or relatively independent things that you're looking for, now your decision is, well, how do you combine these things? Because, and James, correct me if I'm wrong here, you can really only give a scalar. You can give it a number for the most part on that rollout. How well did you do? So if it did really well in one axis and really poorly in another axis, now you have to combine those things into a single number. So I'm curious, James, how you would think about the reliability of a reward model.
Yeah, yeah. I think it's like it's a huge field, right, of like reward design here. And like you mentioned, there's a sort of um like distilling everything down into like a single number, right? Can kind of mask things, right? And then maybe you want to start thinking about like how can you actually design the curriculum, right, to expose the factors, right, that are summed up and canceled out there, right? How can you expose those to the training process in isolation, right? Then you get some signal right? That aren't just like, getting canceled out there, but it really depends on like your use case and it's a pretty sophisticated field of study at this point.
It is. And yeah, like many things that we do at Fireworks, there's always going to be 10 levels deeper, and we are going to do our best to go to all of them and post about them in our blog. Couple more questions. Roughly how much does it typically cost to run an SFT or fine-tuning job on Fireworks? Now, that's always going to depend on how much data that you're using, and the prices for token training is on our website. But to put a finger in the air here, what I did on my notebook cost me, with all experimenting, trying different parameters and trying different hyperparameters, different knobs and levers, all in all would have cost me under $60, which yes is money. I am aware. But when you're talking about training one of the largest models on the planet to do my custom task with my intelligence, it's frankly a small price to pay. And if this is something that your company is footing and your organization really cares about, that's a bill that is going to be, much more compounded in value going forward. James, do you want to add to that?
Yeah, yeah. One thing I would add to that is like with our training platform at Fireworks, we have multiple different like approaches that you can use that depend kind of like on like Sinan mentioned, your data volume, right? Or like whether you can saturate capacity. So what I mean by this, oftentimes when you're doing reinforcement learning, actually you're taking like only a few examples, right, from like, rollouts, and then you're updating the model to do that for efficiency purposes, like usually what will be cheaper here is using a token-based like model because you're not paying for like idle capacity or capacity for which like the GPU is not like saturated. On the other hand, right, if you're doing something where you have a large volume of data, for example, if you're doing mid-training SFT, right? Like, or even pre-training, right? We also sell like training capacity by GPU hour. And oftentimes, like you'll see, if your data volume can keep like those GPUs saturated, you're getting like, a much lower price per token because of, kind of the inherent skill efficiency. So we've got the whole spectrum available for you.
Agreed. All right. Let's go ahead and wrap things up where we are coming up on an hour and a half, and we started a little bit late, but I think I want to make sure that we're all getting out of here in time for lunch if you're on the West Coast, or in time to wrap up your day if you're on the East Coast or wherever you are in the middle. So thank you all for being here. Just to kind of give you an update on what's coming up. Again, this Thursday, we're doing a joint webinar with Arise AI. And you can find that information both on our website, on Arise's website. August 18th is the first cohort of Fireworks Academy. You cannot find this information anywhere yet because you are literally the first people to hear about it. If you do want to learn more about Fireworks Academy, you'll be able to find that information eventually on our website and our blog. And our socials, and if depending on if we can get the links together in time, it can be included as well in our wrap-up email. But look for more information on us from us on that in the short term. Where we'll do Inference 101 first, and Training 101 will start in September. And then lastly, our next scheduled webinar, who knows, because we like to do these and when important things happen, is August 20th. So if you are interested in a certain topic and you want to potentially, reach out to us, you can either find me on Twitter or LinkedIn or email devrel@fireworks.ai. I want to hear what you want to learn. What's top of mind for you? What could we help you understand a little bit better? We shape these after what will help you the most. So with that, James, thank you so much for being here. I hope you had a good time. Did you have a good time?
Oh yeah, absolutely. Yeah.
Great. I think we all had a great time. Thanks so much for being here, everyone, and we'll see you at the next one. Have a good one.
Bye.